I have a note kept on it. For those who are teaching, and if you require a particular slide expanded, just let me know. I just need to look at, I don't know how university is going to look at teaching resource being shared with another teaching institution, but certain section of it I can anonymize it and send it to you in a different email. And I don't think university really minds it, but the copyright material they might require you to remove it. Because we're allowed to, anything online or anything printed, we're allowed to put it in our slides under our copyright agreements. But if we transfer it, that copyright agreement stops at the time I transfer it. So you will then become liable if you use it, unless your institution covers it. So that's why they will be careful. Okay. So durability testing and all of that, and then the chloride, the carbonation modeling, I put my Excel file in it. You can have a look at it. And I will change the variables in that Excel. I have changed the different variables, and all of the time I'm trying to figure out which variable is more significant, because that is the variable that I really will have to define, either through testing or through more research. Okay, so this is one way. This is quite an easy comparison way of doing it. There's a mathematical way of doing that as well, if the model is very complex. That's what structural engineers do in certain cases. And we're going to look through life cycle costing and all of that today. Anything which has an L prefix is a literature article. Most of it is from our work because it's open access publication, so I can give it to you for free. Some of it, for example, if I go down, the last one is the principal component analysis. So that's the mathematical approximation of figuring out which variable is significant. You should only go that direction if you're handling a massive project with a massive durability concern with it, and you can invest the time. It is a very complex process, but it will make your life easier if it's a bigger project. It's the start of it. It's on the chloride transport we were looking at. You know, the models that we use have 40 variables. It's not realistic, so we were trying to cut down to maybe 5 or 6, and that's the example of how it's a published article. The next one is sacrificial anodes. Those who are interested in the anode system, the performance of it, we were asked to study the performance in the laboratory system for a particular structure. So this is the example of that. So it's a publication. We're going to look at repair concrete and the performance of repair concrete using sensors. That's also a published article. I'll use a presentation to show you the actual figures, but anything that's published is given here, so you can have a look. So the factor-based method we covered yesterday using half cell and resistivity and diffusivity, that publication is here. So, happy enough? Anything else which is not here, just ask me. I can give you my email. Okay, so the emails in our university is first name dot surname at QUB for Queen's University Belfast.ac.uk, and that'll be the same for any person that you're looking for. Their first name dot surname at what university, say Leeds, and it'll be Leeds at .ac.uk. Unless there are two people of the same name, then it might actually have different initials coming in. Okay, happy enough? So you have the USB file. Yeah. Okay, so I'm not going to go too far into this. So yesterday we looked at the Duracrate carbonation model. Similar to that, Duracrate has a chloride model. Okay. Download the Duracrate report. You will get a list of variables that you can use with that, and then you can use the model. Okay. This is not the complex model. Chloride environment has a lot of different people of different skill set. and a lot of them use very, very complex models. Okay? I don't think it's necessary, but I think this is sufficient. Because anything that you're dealing with engineering, it's an engineering structure in meter scale. It's not a structure that's in micrometer or nanometer scale. Those nanometer and micrometer should be used for studying material technology or interfaces or properties. It shouldn't be used for engineering modeling and large scale. Okay? And I don't think they're in a capacity to do that either. So if you look at anybody looking at cement particle modeling, they don't come to concrete. They can't, because the scale is tremendous. That kind of capability is not there. Might come in the future, but the intensity of work it's required is prohibitive enough for it that it can't come up. So I prefer models like that. We're in the process of, the 40 variable model that I've talked about, we're in the process of making that available publicly. And I need to ask Professor Tang Looping from Sweden. But when we make it public, we will limit a lot of those variables. We'll still make it visible, because I think that's critical, because people need to know how this works. But we will make everything gray except the cells where people need to change. Okay. In that way, we're just saying, look, as long as you get these variables, mathematically we can say they're significant. So if you change those variables, you get a reliable result. If you do want to go and change all the variables, open the cell up and do it yourself. Tang is open to the idea, but I just need to make it, we're still working out on what's the best way to publish it, because it's between different universities. Professor Looping is from Chalmers University in Sweden. We're trying to figure out who owns the liability and that kind of stuff. It's a bit complex stuff. Okay, so I'm going to leave that there. So you can try the chloride model using an Excel file. It'll look exactly the same as what you've done yesterday.
What is CX?
Cx is the chloride concentration at a depth. Okay? So the equations that you look in literature will say Cxt. That is mathematically correct. Okay? But Cx represents the depth x. Okay. When you put that equation into Excel, what you will get is chloride concentration percentage by weight of cement or concrete. That's determined by what is your surface chloride concentration. If you express your surface as percentage by weight of binder, then that's what you're going to get, cement. If you express that as percentage by weight of concrete, then this is what you will get. Okay? And you're going to get an equation like that, okay, where this will be x depth The ERF is an error function. Excel has an error function built in. So just type equal to ERF. It'll open up the error function. And everything else is the same. Sorry? Yeah, they can do that exercise. Do you want to try the exercise and then bring it tomorrow? Okay. And then I can have a look and give you comments on it. So these Cx values, so this is the Cx for x is equal to 1. So when you put x is equal to 1, you get that value, which is that Cx. So x is equal to 5, this means this is C5. Okay? And this graph is for a time. Okay? So it's very, very simple. And which way would the graph go, or which way do you expect the graph to go when time is 5? Do you expect the graph to go this way? Do you expect the graph to go that way? I'm going to draw two graphs. You can tell me where the graph is going to go. T is equal to 10 years. This is T is equal to 10 years. Which one is correct? A or B? True. Okay. Chloride concentration in a concrete will always increase with time. Okay. Given there's no chlorides going out of the concrete. That can only happen if your concrete already had a lot of chlorides. Okay. So if you make a concrete out of no chlorides in it, external chloride concentration, because of the larger concentration on the surface, will try to go into the concrete. Okay. For those who know this differently, the area under this graph will give you the total chlorides in up to that depth. Okay. So the total chloride will always increase because there's concentration outside, there's not enough concentration inside, so chlorides will always move, which means with time you're expecting the graph to go up and up and up. The critical part to you is, where is your rebar? If your rebar is here, that means, and this is your threshold, which means T1 is okay, but T10, the threshold has been exceeded, so you're likely to get corrosion probably about 5 years time. Okay. It could be 10 years, it could be 50 years, depending on the variables. And that's how you use the graph for your benefit. Okay. And this is where I said I'll use the best in the worst case scenario. I will create the best in the worst case by changing the diffusivity, changing these factors. So one of the factor is curing. So I have a concrete that I cured it perfectly. Okay. Perfect curing for me is long-term water-based curing or moist environment curing. I do not by any means to say steam curing or microwave curing or anything like that. Long-term stable curing is good. All of these accelerated curing methods will help you to achieve normal curing that you cannot achieve otherwise. So for example, a very dry open site, you will need to look at some form of curing so that you get normal curing that you would have achieved otherwise. For perfect curing, you just need to wrap it up with the wet hessian, keep it moist for as long as you can.
How much long?
As long as you can. So it takes, within 2 years, we've looked at different cement systems. Okay, so one was a normal Portland cement, and one was a heavy blended cement with very much like 79% replacement. Normally, the 79% replacement will give you low diffusivity much early on because of all the reactions happening, and the microstructure will refine further and further, which is great. But the Portland cement we decided to cure for 2 years, and the blended cement we also cured for 2 years. What we found is the reduction due to curing in Portland cement was significant. It doesn't reach the same as the blended cement in no way, but it has the potential to go closer to it. It clearly was better than the 28-day values. Let's see if I can pull the presentation and you can have a look. So curing does have a role to play. The old money, I think people would have cured concrete much longer. So the farmers in Northern Ireland, they would have cured their concrete slats that they use for silage. Does silage make sense here? Silage is the grass cutting. They use silage now to make electricity by just biogas kind of system. So silage cutting and the waste streams from the cattle slots, they all come in together, and then they put a biogas plant, they make electricity from it. It's called anaerobic digestion. Okay? But anyway, those silage are, the grass cuttings are low pH, they're between 4.5 pH. So the surface that they put it on concrete areas like massive silage pits, and it's naturally sloped gently to get the water out. And this water is in pH 4. So when that water slowly drains, in Ireland it rains all the time, so when it generally drains, it takes the cement with it. So none of the new cements that we know, not cured properly, they won't last. So farmers in the past would have put a tar coating on their concrete, and that'll last for 2 years. And it'll naturally wear off, tar will wear off. But by the time 2 years elapse, their concrete is super. It doesn't really, because it had the time to cure itself before it's been exposed to all this nasty chemicals. So answer to curing is as long as it can. Concrete has the ability to cure itself because you would normally add enough water in the mix anyway. According to Neville, 0.26 water binder ratio is all that you need for curing. So if anybody says their water binder ratio is 0.2, I don't know how realistic that is. 0.2 is extremely low. It shouldn't really happen because it's not a workable mix unless it's heavily chemical based stuff. So 0.26 is what you need. I prefer anything close to 0.4 because engineering wise that's more reliable. I can spray it, I can mix it, I can flow it. Which means it has enough water. So seal the concrete as early as you can so it has the moisture within to cure itself. And the seal